Welcome back to another episode of Data Deep Dive. Today, we're diving into the fascinating world of Mapreduce and its pivotal role in batch processing. Whether you're a data engineer, a developer, or just curious about how big data gets processed, this episode is for you. We'll unpack some key concepts, discuss strategies for optimizing data joins, and explore how Mapreduce fits into the broader landscape of data workflows. Let's start with the basics. Mapreduce is a programming model designed for processing large datasets across distributed systems. It breaks down tasks into smaller subtasks, which can be processed in parallel. But with this power comes complexity. One of the significant challenges in using Mapreduce is efficiently joining datasets, especially when dealing with large volumes of data. When datasets are joined in a traditional Mapreduce job, it involves sorting, copying data to reducers, and merging inputs. This process can be resource-intensive, leading to increased costs in terms of time and computational power. Fortunately, there are ways to optimize this process. One effective method is the map-side join. This approach eliminates the need for reducers and sorting, allowing each mapper to read a block of data directly from the distributed file system and write the output back without the overhead of a reducer. Think of it as a streamlined process where each mapper handles its own small dataset, making it much faster. For this to work, the smaller dataset must fit entirely into memory. When a mapper starts, it loads this small dataset, like a user database, into an in-memory hash table. As the mapper processes the larger dataset, such as user activity events, it can quickly look up user IDs in that hash table, resulting in a much faster join operation. This method effectively broadcasts the small dataset to all mappers, ensuring that each one has access to the necessary information without needing to repeatedly access the distributed file system. Tools like Pig, Hive, and Cascading support this approach, making it a popular choice in data processing workflows. Now let's take it a step further. If both datasets are partitioned based on the same key, we can use a partitioned hash join. This means that each mapper only needs to load a smaller partition of the data into memory, further reducing resource usage. For example, if both datasets are divided based on the last digit of user IDs, each mapper can focus only on those relevant records, making the process even more efficient. Another variant is the sorted join. If the datasets are not only partitioned but also sorted by the same key, mappers can perform merging operations that would typically be handled by reducers. They can read the input files in order, matching records with the same key as they go along. This method can be particularly powerful if the datasets were pre-processed to be in this form. The structure of the output from these joins also varies. A reduced side join will produce output that is partitioned and sorted by the join key, while a map side join maintains the partitioning and sorting of the larger input. This distinction is crucial for anyone looking to optimize their data processing workflows. Now let's step back and consider the broader context of batch processing. Unlike transaction processing, which focuses on quick lookups of individual records, batch processing often involves scanning large datasets for analytics. This could mean generating reports or preparing data for machine learning systems. Google famously used Mapreduce to build search engine indexes, demonstrating its power in managing large volumes of data. By partitioning documents and having reducers build indexes for each partition, they could efficiently manage and update their search indexes. However, there's also the option for incremental indexing. Instead of rebuilding the entire index from scratch, systems like Lucene can add, remove, or update documents incrementally, which can be more efficient when only a small portion of the dataset changes. Once the batch processing is complete, the question arises, how do we get this data back into a database for querying? While it's possible to write directly to a database from within a Mapreduce job, this approach can lead to performance issues. Making individual network requests for each record is slow and can overwhelm the database, causing operational problems. Instead, the best practice is to write output as files to the distributed file system. These files are immutable and can then be loaded in bulk into the database, ensuring that the database can handle read-only queries efficiently. This method also provides a clean, all-or-nothing guarantee for job output, which is crucial for maintaining data integrity. Many key-value stores like HBase and Voldemort support building database files through Mapreduce jobs. The beauty of this approach lies in the simplicity of the data structures involved. Since the files are immutable, switching from old to new data can be done atomically, ensuring that any issues during the process can be easily resolved. In summary, understanding the nuances of Mapreduce and batch processing is essential for anyone working with large data sets. By leveraging techniques like map-side joins, partitioned hash joins, and efficient output handling, we can optimize our data workflows and improve performance. As we continue to explore the world of data, remember that the right strategies can make all the difference in how we process and analyze information. Thanks for tuning in to this episode of Data Deep Dive. If you found this discussion helpful, be sure to subscribe and join us next time as we explore more exciting topics in the realm of data processing and analytics.